A robot is an automated machine, but it is different from other automated machines in that it is designed to perform multiple tasks rather than a single task. A robot can be programmed to perform tasks in different ways or to perform entirely different tasks. There are many different types of robots, with 4 primary ways to classify them: stationary or mobile, number of axes, type of motion, and servo or non-servo. A stationary robot is attached to a fixed surface such as a floor, wall, or ceiling. Typical applications of stationary robots include welding, painting, assembly, pick and place, packaging, and palletizing, product inspections and testing. Mobile robots can move from one place to another. This may be to increase the size of their work envelope or to transport materials. A robot axis is a linear or rotary direction in which the robot arm can move. More axes allow a robot more freedom of movement. By ISO definition, industrial robots must have 3 or more axes. Most industrial robots have between 3 and 6 axes. Robot joints can move in one of 2 ways: straight line or linear, and rotational, also referred to as articulated. A servo-controlled robot controls the speed and position of its axes through its program. It uses sensors that continuously feed back axis positions, enabling the controller to precisely stop the robot in any position. A non-servo robot uses a more basic controller method that controls axis position with hard stops on each end of travel. Limit switches are located at each hard stop to signal the control to sequence the next move. Servo robots can be programmed to move to many more positions in a program than non-servo robots. Non-servo types, also called pick-and-place robots, are used for simpler tasks. Servo robots are made in a variety of styles to meet the needs of many different applications. These styles vary by number of axes, type of motion, and whether they are mobile or stationary. There are 5 common types of motion used by servo robots: articulated, Cartesian, gantry, Scara, and delta. Articulated or jointed arm robots mimic the form of the human arm. These robots use rotary joints, and the number of axes corresponds to the number of joints when the arm can twist or bend. Articulated robots are very good at reaching in and around objects. They are the most versatile robots, and their applications include welding, material handling, assembly, painting, palletizing, and machine loading and unloading. Cartesian robots are also called linear or XYZ robots. They use three linear axes that are at right angles to each other, like the X, Y, and Z axes of the Cartesian coordinate system. They may also have an attached wrist to allow rotational movement of the end effector. Common applications include picking and placing parts on a conveyor and assembling parts on a circuit board. Gantry robots are Cartesian robots with the horizontal members supported at both ends, so the arm is positioned overhead the workpiece. They can be very large and can handle very heavy loads. They are used in aerospace industries to lay down layers of composite materials on wings. SCARA, or Selective Compliance Assembly Robot Arm, robots use two rotary axes in the same plane and a third axis that moves the end effector up and down. They may also have a fourth axis that allows the end effector to twist around that vertical axis. They are commonly used in assembly applications for small components such as cell phones and watches. Delta robots, also known as spider robots, use three middle-jointed arms connected to universal joints at the base. A fourth arm in the middle, connected to the same base, allows the end effector to rotate. The arms are joined together at the end effector, which can only move in a horizontal plane. However, the joints in the arms allow it to be positioned anywhere on that plane within the robot's reach. Delta robots are heavily used in food, pharmaceutical, and electronics industries. They are especially well suited for super high-speed, pick-and-place applications with relatively light loads. Identify each type of servo robot. Although servo robots are available in many different styles, they generally consist of the same major components and operate in a similar manner. The major components of all servo robots include manipulator, end effector, controller, drives, offline programming device, teach pendant, servo motors, encoders, and home position sensors. The manipulator, also called the arm, is the part of the robot that actually moves and reaches. The end effector is used to grasp parts or manipulate tools. One type of end effector is the hand or gripper, as shown. The end effector can also be a tool that enables the robot to perform a specific type of task on an object, such as drilling, welding, or cutting. A controller is the specialized computer that coordinates a robot's movements. It is where the robot program is stored and executed. Drives are electronic circuit cards in the controller that supply power to the robot's motors. An offline programming device, often a PC, is used by a person to create programs that will later be downloaded into the robot controller. A teach pendant is a handheld control device that is connected to the robot either wirelessly or by a cable. The teach pendant can be used to manually control the robot, edit the robot program, and enter new programs. Servo motors are electrical motors that are connected to the robot's arm. Servo motors are specifically designed to be able to move their shaft at a specific speed and stop at a precise position. Encoders are electronic devices attached to the servo motors that allow the controller to monitor the position of the servo motors. Home position sensors are used to reset the encoder values stored in the robot controller whenever the robot is homed. The controller uses the home position as a reference when it moves the robot. To perform tasks automatically, robots require a program file to be stored in their memory. The program file contains a series of commands that create the robot's sequence of operations. A separate command is used for each step performed by the robot. In this simple example, the robot program consists of 4 lines, each commanding the robot to move to a specific point. When the robot program is run, it performs the commands in sequence, starting with line 1. Once each command is completed, the controller executes the command on the next line. The servo robot uses encoders on its axes to determine when the arm has reached each point. Robot programmers often refer to the positions to which the robot will move during operation with general names such as point 1, point 2, and so on. However, to move the arm to a point, the robot controller must know the encoder values of the axes. For each point in a program, the robot controller must have a value stored in its memory for each of the encoders. For example, a 5-axis robot requires 5 encoder values to be stored in memory for each point. The memory locations where these encoder values are stored is called the points file. In this example, the points file consists of 4 points, each with 5 encoder values. The program file can make use of each point as many times as necessary during each cycle. Before a robot can run, both the program file and the points file must be loaded into the controller. When started, the robot will follow the sequence of steps in the program file, moving to the encoder values listed for each point in the points file. When a command to go to a point is executed, the robot controller causes the axes motors to rotate until each encoder value matches the value stored in the points file. At that point, the robot has reached the programmed point. Points can be entered into the robot control. Keypads allow the robot to teach pendants are typically comprised of the following components: display screen, emergency stop push button, keypad, and housing. Display screens provide the robot operator with a series of menus and functions. The menus and functions on a Teach pendant usually include the most common functions used to remotely operate the robot. An emergency stop push button is included on the robot Teach pendant. When pressed, the emergency stop push button stops any running programs and immediately disables all robot drives. Keypads allow the robot operator to enter and display information about the robot's operation. Some keys are assigned one specific function, whereas other keys, called soft keys, can be used for many functions. The housing is usually a hardened plastic enclosure that contains electronic components and protects them from the environment. To teach points to a robot, first move the robot arm into a certain position, then press the Teach key on the Teach pendant. Teaching is by far the most common way to program servo robot points. It is a very accurate way to build the points file, since you can see where the robot is for each point. You never have to know what the actual encoder values are for each point, because the controller does this work for you. Most industrial robots have between 3 and 6 axes. On an articulated robot, these axes are divided into two classes: body axes and wrist axes. The purpose of the body axes is to move the end effector to some point in space. These axes are named for the human counterparts they resemble: waist, elbow, and shoulder. The waist axis rotates the arm horizontally. The shoulder and elbow axes control the height and reach of the arm. The body axes define the reach of the robot in all directions. This is called the robot work envelope. The robot cannot reach any objects or positions outside its work envelope, so all parts, fixtures, and machine access points must be within the robot's envelope. Each style of robot has a different envelope shape. This shape often makes one robot better than another for a given application. The wrist axes allow the robot to orient its end effector so it can position a part or tool. These axes are named using nautical terms that describe how a ship moves in the water. Pitch tilts the end effector up and down. Yaw, if available, turns the end effector left and right. And roll turns the part over. The end effector itself is not considered an axis. For example, a 6-axis robot has 3 body axes, 3 wrist axes, and an end effector. Many articulated robots are attached to a linear traverse axis that moves in a straight line, allowing the robot to have a larger reach. The traverse axis allows the robot to increase its work envelope at a lower cost than using a larger robot. Linear axes are often used to load and unload multiple machines. A linear axis is considered to be part of the robot, so it adds to the total number of robot axes. For example, a 6-axis robot with a linear axis is a 7-axis robot. Identify the axes on the robot and the robot arm. Identify the axes on the robot and the robot arm. Like many other automated machines, robots do not work alone. They work with tooling, fixtures, part feeders, and even other machines. The robot's work envelope and the equipment within it is called a work cell. Robot work cells can be very dangerous places for humans because the robot and surrounding equipment can generate high speeds and high forces. As a result, work cell safety is very important. The work cell must be designed so people cannot enter the robot's work envelope while the robot is operating, and devices must be available to stop the robot motion at any time. Examples of devices that protect people from injury by robots include emergency stops, dead man switch, barricades, light curtains, safety mats, signs and tape, and collaborative robot systems. An emergency stop push button interrupts power to all parts of the robot work cell, including the robot and the equipment inside the work cell. Emergency stop push buttons are located on the teach pendant and robot controller, as well as other locations around the work cell. Some robot teach pendants are equipped with a dead man switch to safeguard the operator when teaching the robot. A dead man or enable switch is a 3-position switch that must be held at the correct pressure while manually operating the robot. If the switch is not held, it is assumed that the operator is not in control of the pendant. If the switch is held too tightly, it is assumed that the operator is in pain. If either condition occurs, the controller stops the robot. Physical barriers are used to protect people from robots. Chain link fencing or walls around the work area of the robot can be used to restrict access to the robot. Barricades typically have a gate with interlocks so that the operation of the work cell stops if the gate is opened. Restarting the operation requires closing the gate and pressing a control switch outside of the barrier. Some factories limit access to the robot work cell using beams of light. These focus light beams are positioned to form a light grid or light curtain. When interrupted by a person entering the guarded area, the light curtain acts like an emergency stop push button and stops the robot. Another popular safety measure is the electric safety mat. These mats are designed with embedded switches that shut down robot operation when someone steps on them. Warning signs should be placed around the robot work cell. The floor around the robot work cell can also be marked off with black and yellow tape to help direct traffic around the hazardous area. Collaborative robot or cobot systems are designed to operate safely in the presence of human workers. Some cobot systems can detect when a person is near the robot arm, or if the arm has touched a person. If a safe distance cannot be maintained, the robot shuts down. Many cobots have soft padded arms without any pinch points to minimize the danger to humans working near them. Cobot systems are used in many areas, including machine tending, heavy lifting, and product packaging. Robot work cells can be very dangerous if safety rules are not carefully followed. Robots can create high speeds and high forces. They can start, stop, and change direction suddenly. Robot safety rules begin with using correct dress code. The dress code for working around robots is the same as for working around any automated machine. This code applies to robot operation, teaching, and maintenance. It includes rules for these items: eye protection, clothing, jewelry, hair, footwear, and gloves. Wear properly fitting approved safety glasses with side shields. Wear close-fitting clothes. Remove ties, rings, watches, and other jewelry. Tie back long hair or tuck it into your shirt or hat. Wear proper shoes to protect your feet. Do not wear gloves around a machine that rotates or has heavy moving parts, including robots. If the environment requires gloves for some other reason, such as sharp edges, chemicals, or temperature, wear tight, form-fitting gloves of a type chosen to reduce the risk of entanglement. In addition to observing the dress code, there are 5 important rules to follow if you operate a robot or will be near a robot that is operating. Observe a robot safety system. Locate emergency stops. Monitor controls. Monitor nearby personnel. And complete safety training. During normal robot operation, the operator must stay out of the robot's work cell so that the barrier and/or presence sensing systems are not tripped. Under no circumstances should any interlock mechanism be removed or bypassed. The operator must know where all emergency stops are located. Emergency stops must be readily available in all zones as well as the teach pendant, and they must override all other controls. The operator should monitor the robot's operating and fault status. The operation status is often displayed on a human-machine interface, or HMI, located outside the work cell. Controls that initiate power or motion must be guarded against accidental operation. The area around the work cell should be clear of untrained people or people acting in an unsafe manner. Before starting the robot, operators should check for personnel in the area and notify them that the robot is going to operate. Robot operators, programmers, and maintainers must receive adequate training in hazard recognition, control of robots, and proper operating procedures, including safe work practices. Teaching points with a teach pendant requires the operator to be inside the work cell to view arm positions up close. To do so safely, follow these additional safety rules. The worker must carry the teach pendant in order to have immediate access to the emergency stop button. The robot must be in the teach mode. A slow jogging speed must be set. And another worker should observe the robot and press the emergency stop if necessary to protect the worker. Robot maintenance includes periodic preventive maintenance checks and repairs after a failure. Both types of maintenance should only be performed when the robot work cell is locked out using the OSHA-approved lockout-tagout procedure. The lockout-tagout procedure should be performed on the disconnect switch that controls all power to the work cell. The role of a robot work cell operator includes powering up and powering down the work cell. Work cells often include other devices in addition to the robot, so the power up and power down procedure will vary from one cell to another. The first part of powering up a robot is to perform a safety pre-check to make sure the work cell and operator are prepared for safe operation. This pre-check typically includes operator properly dressed and trained, work cell clear and clean, equipment checked, safety device operation verified, lockout-tagout verified, and nearby personnel notified. The operator must fully understand the robot's operation and the associated safety rules. The operator must observe safe dress rules. The work area must be free of untrained or unsafe people. All obstructions must be removed from the robot work area. The work area must be clean and dry. The teach pendant and all other tools must be in their designated places. The robot, other equipment, and wiring must all be free of damage. There cannot be any air or oil leaks. The operator must know where the emergency stop buttons are located and check them for proper operation. The operator should push and pull all of the emergency stop push buttons to verify that they operate. The operator should verify that lockouts-tagouts are present. The lockouts-tagouts should not be removed until the operator is beginning the power-up process. The operator should notify nearby personnel that the robot is about to be started. To power up a robot, these steps must be performed. Remove the lockout-tagout on the robot's circuit breaker and turn on the circuit breaker. Turn on the robot controller, which also powers the teach pendant. Select the teach pendant options on the controller and the teach pendant so that they communicate with each other. Enable the drives if they are not automatically enabled. Home the robot if the robot does not have absolute encoders. And verify that all screens appear with no faults. Robots with absolute encoders do not have to be homed. They retain their encoder values while the robot is powered down, so they always have valid reference values. To power down a robot, 3 steps must be performed. Move the robot arm to where it is to be positioned while not in use. Turn off the power switch and apply the lockout-tagout. Some robots relax after they are powered down, but most have brakes that keep them in position. After the robot has been powered up, the operator must often jog the robot. Jogging means to manually move the robot arm to a new position while under power. There are 3 reasons to jog the robot: startup, teaching, and shutdown. Before the robot is put into operation, the arm should be jogged to a safe position. This start position makes sure the robot is free to move and will not hit any obstacles. Teaching is a necessary step in the programming of a robot. The robot should be jogged into a desired position to record the encoder values in memory. The robot should always be jogged to a safe position before shutdown. This position should be where it will not hit obstacles when the drives are disabled and the arm relaxes. A teach pendant is often used to jog the robot. For example, the teach pendant shown has a jog button on it to select the jog operation. Some teach pendants have a button that allows the operator to select a slow or fast jog speed, and another button that allows the operator to select the jog direction, left or right, up or down. Individual buttons allow the operator to select the axis to jog. There are times when it will be necessary to stop the robot with an emergency stop, which immediately interrupts the robot. Pressing the emergency stop push button causes the robot to stop mid-motion and removes power from the robot. Dynamic braking systems hold the robot in place. If the robot is stopped using an emergency stop, the operator must verify that the reasons for the emergency stop have been corrected before any attempt is made to restart the robot. An emergency stop push button is a mechanically latching push button, so it stays depressed once it is pressed. The emergency stop push button that was used to stop the robot must manually be pulled out to enable restarting. This action does not restart the robot. After the emergency stop push button is reset, the robot drives must be reactivated and the robot must be homed. Then the robot can be started normally. Computer. In this procedure, you will perform the steps to complete the following tasks. You will start the Pegasus control software and explore its different areas. You will also activate and explore Pegasus RSS. You will perform the steps necessary to power up and shut down the Pegasus robot. These steps are to perform a safety check, turn on the power, and enable the drives. You will jog the robot using the teach pendant with the fast and slow jog speeds. You will jog the Pegasus robot using the Pegasus control software. And you will change fast and slow jog speed settings. Click on the computer to view the step-by-step instructions for performing this procedure. After power-up, many robots should be homed to make sure their encoder values are accurate. If the encoder values are not accurate, the teach points will not be correct and the robot will not move to the correct positions. Homing is an automatic procedure that moves the robot's axes to the positions where they actuate their home position sensors. The controller then resets its memory for each encoder position to 0. This calibrates the access encoders and makes sure that the robot will accurately go to each position stored in memory. Robots with absolute encoders do not have to be homed. They retain their encoder values while the robot is powered down, so they always have valid reference values. When the robot is first turned on, it should always be homed before it is operated or programmed. Before homing, the robot should be jogged to a clear position so that it will not crash into tooling during homing. Homing is selected with a button on the teach pendant. The robot controller moves each axis one at a time until each axis reaches its home position, continuing until all axes are in their home positions. A typical robot homing process uses the following homing sequence: shoulder, elbow, wrist roll, wrist pitch, and waist. Moving the shoulder axis first helps to ensure that the end effector is clear of any obstructions. The waist axis is usually homed last because it could crash the end effector into an obstruction if the end effector was not already in its home position. When the homing sequence is complete, all of the axes should be in their 0 or non-deflected positions. Place the axes in the correct order for a typical homing sequence. A typical robot homing process uses the following homing sequence: shoulder, elbow, wrist roll, wrist pitch, and waist. Moving the shoulder axis first helps to ensure that the end effector is clear. Place the axes in the correct order for a typical homing sequence. Computer. In this procedure, you will compare two methods to home a servo robot. The first method is the regular homing procedure. This type of homing can take several minutes to complete. The second method, called quick homing, takes a fraction of the time. Click on the computer to view the step-by-step instructions for performing this procedure.